All right, chapters 3 and 4, we're going to be looking at measures of central tendency. These are numbers or words that are trying to talk about the middle and or typical value for distribution. A lot of times we think of the average, but it can be also the mean, median, and mode are the three different things that we're going to look at. The mode is the most frequent score, the one that occurs the most often. There's an example. Okay, so here's an example. So these are the number of years that each president served, the last 20 presidents, how many years they served. Like, so Harrison's the first one. Clinton, so the textbook's kind of old. Clinton was the last one. He served 8 years. Harrison served 4 years. And then we have each president in between those. So that's like FDR. He got to serve 12 years around the time of World War II. In any case, if we're looking at the mode, the value that happens most often, you can look through here and you can see that most presidents are single-term presidents, meaning they serve just one term, which is 4 years. So there's 1, 2, 3, 4, 5, 6, 7. So the mode is going to be the 7 for this distribution. It's also possible that you could have a bimodal distribution where a distribution has two peaks. Generally, we're looking at a standard distribution where there's just one peak, but it's possible you have a bimodal distribution, and this can happen, if you're comparing two different groups and you have them together in the same thing, they could have that bimodal, or in the case of the U.S. presidents, a lot of presidents served 4 years, but there was quite a few that also served 2 years, which was 8 years. And then we also have, again, the outliers here. There were outliers like some presidents that were assassinated or died in office. Nixon, who was relieved of his duty. Ford, he didn't serve for full 4 years, full 8 years, and so that's why we have some of these here in the middle. In any case, 4 and 8 is generally what we think of when we think of the terms of presidents serve, and so there is a bimodal. There's two humps in this distribution. In theory, you could have many modes, like multimodal, but generally we're just going to have one mode, or maybe bimodal. Here's another example of how it could be bimodal. If we took everybody in the class and we measured their weight, and then we looked at that, it might be bimodal because of the gender difference. So men weigh more than women typically, and so it would probably be bimodal based on gender. So we could separate them out, or if we have them together, though, we're probably going to have a bimodal distribution. The median is the middle value when the observations are ordered from least to most. So the middle value. So the median splits observations into two equal parts, the upper and lower halves. So usually that median is going to be at that 50th percentile rank. We talked about percentile ranks last chapter. There's a couple different ways to get to that median. The easiest way, so what you do first is, if this was our distribution, you would take it, put them in order. So here's how we got it originally: 2, 8, 2, 7, 6. Put them in order: 2, 2, 6, 7, 8. And here's the easy way to do it. You just take one off each end. So we mark off the 2, mark off the 8, mark off the 2, mark off the 7. Ta-da! The median is 6. So that's pretty much the easiest way to do it. It'd be a little bit more complicated though if you had, a million numbers. And so there is another way to do it that's a little bit more complex. You take the number of observations that you have. So in this case, it's 5. 1, 2, 3, 4, 5. You add 1 to that to get 6. Divide by 2, which is 3, and then count 3 into your distribution. 1, 2, 3. So again, 6 is the median. I'll say that again. Take your n, which in this case is 5. Add 1 to get 6. You take that 6, divide it by 2, and you get to which is 3, and then you count 3 in. 1, 2, 3. You may have a distribution that's an odd number, and in that case, so if you take off the ends, 1, 9, 3, 8. We're left with 2 in the middle, the 3 and the 8. Add those together, divide them by 2. So 3 and 8 together is an 11. Divided by 2, 5.5. So our median, although it's not technically one of the numbers in the distribution, our median is going to be 5.5 for this distribution. The mean is probably the one that you're most familiar with, and probably the one that you use most often when you're trying to calculate your grade. You're trying to get to the mean. So the mean is found by adding all scores together and then dividing by the number of scores. So in our president example, again, if we added all of these together, 4 plus 4 plus 4 plus 8, we add all those together, we're going to get 112. Again, the n for this was 20, so we would take 112 divided by 20, and we're going to get 5.6. So for the 20 presidents during this time period, The average number of years they served was 5.60. Okay, so that's pretty easy. The means, when we're talking about means for a sample or means for a population, we do have different symbols that we're going to use. And so one of the reasons this is going to be important is later on we're going to have some different symbols and some slightly different formulas when we're looking at the difference between populations and samples, which we did discuss in the last lecture. The population, complete set of scores. Sample is the subset of scores. So, and again, it can be kind of abstract, and it kind of depends on your perspective and what you're looking at. So all students at Northeastern, you could call that a population. The students in this class, we could call it sample. The students in this class are a sample for all students at Northeastern. And even in this example, so this is actually a population. We just wanted to look at the last 20 presidents, so that is a population. It's technically, if you look at it from a different perspective, it would be a sample of all presidents but we just wanted the last 20, so that's a population. It's the complete set of scores. So again, it's kind of about perspective. All students at Northeastern is a population. In the example I gave, it could also be a sample of all college students. So why does this matter? Not only would it matter, it's about perspective, and that distinction is going to matter later on, because when we're talking about populations, generally we're not going to know the mean for a population. Like if you talk about all Americans, we're never going to get all Americans on anything, even taxes. We're not going to get everybody. So the population is usually unknown. In the sample is going to be known. We're going to get our sample and we'll know exactly what it is, but it is going to vary from sample to sample. If you take 10 random people and get a sample from them, you'll get 10 other people, get a sample from them. It's going to be different. So the population is going to be unknown, but usually we'll consider it to be fixed value. And the samples are going to be known, but they're going to vary from sample to sample. Generally speaking, we are dealing with samples. It's rare that we're going to deal with populations. So all that being said, the formula to get the mean for a sample, this is what it looks like. The way you say this is x bar. X bar equals the sum of the variables of x and is divided by the sample size, which is n. So in that president's example, when we added all those numbers up, the 4, the 4, the 4, and the 8, that is this here, the sum of the variable x. You take all of the x's, add them all together, this is sum, and divide it by n. It's a small n. In the sample, it's a small n. You divide it by that 20, and that gives us the average, the x bar. The population mean, this is what the formula looks like for that. Instead of having x bar, we have it's pronounced mu, and this is what it looks like. And it is, again, the sum of x, and it is divided by the population size, which now, instead of being a small n, is going to be a large n. In this case, again, it's essentially the same formula. It's just that the symbols will change. But again, that'll be later. That'll be important later on in some of the other chapters. It's kind of neat when you think of the average. So the average, this is the president's example again. The average number that they served was a 5.6. So, it's somewhere in here. You can think of the mean as a balance point for the entire distribution. So if the distributions were like, if there was weights put on each one of those, so each one of those actually equaled a weight, and it would balance out at that point of 5.6. And so, yeah, it's kind of a neat way to think about the mean. And then we have to have all of this on this side to balance out that 12 that's way at that other end. And we'll talk a little bit about outliers and how they can influence that balancing of that balance point. If the data, when we're talking about which average to use, and so when we say average, we are talking about the mean, median, and mode. If the data isn't too skewed, the mode and the median and the mean are all going to be fairly similar. If the distribution is skewed, though, those are going to start to get off. The mean is the most sensitive to outliers. Mean's most sensitive, the median and mode are less sensitive. So in this example here, this is country rates, infant deaths. And so if you look, there's quite a few countries that have pretty low numbers, and then, it gets up a little bit bigger than here. Once we get to Cambodia, there's a giant uptick in those numbers of infant deaths, and then by the time we get here, it's incredibly large compared to Sweden or Japan. So if this data is skewed, we do want to report the mean and the median, so people have an idea. It's like, oh, something's a little bit skewed here. So for example, in this data, the mode is a 4, and you can see that. The one that occurs most often is 4. 1, 2, 3, 4, 5. We have 5 4s. The median, if you were to line them all out, would be a 7. So here's about the midpoint, 7. The average, though, you might think about it. What do you think the average is? Got the mode of 4, median of 7. The mean for this one is 30. 30 is considerably larger than 4 or 7. So if it's a kind of a standard distribution, your mean, median, mode will all be pretty close together. But in this example, that mean is way at the other end. So that's a big difference. So yes, when you have that big difference, you want to report that mean of 30, but you also want to report that median of 7. So that lets us know, okay, there's a pretty big difference there. And so let's say you're just reading the numbers and you're like, I see the mean, I see the median. Can I tell which way it's skewed? You actually can. And so if the mean is bigger, greater than, the median is going to be positively skewed. So like in our example there where the mean's 30, the median was 7, it is positively skewed. A few numbers that are in the positive tail. If the median is bigger than the mean, then we have it's negatively skewed, meaning there's just a few values that are here in this negative tail. And again, just so you know, when we say average in statistics, we are technically talking about the measures of central tendency, so mean, median, or mode. Most of the calculations, though, we are going to be talking about the mean. And so if you say average and mean interchangeably, that's acceptable. When you're looking at the averages for qualitative and ranked data, you can always use the mode, the one that occurs most frequency. So this is from last chapter, that Facebook data where there was a survey and it was yes and no. The mode clearly is yes because it's the one that happens most frequently. For qualitative, sometimes you can also use the median. If the data is ranked ordinal, like military rank from last chapter 2, you can get those relative frequencies, get the cumulative percentages, and then you get up to 50. You can say that that's where the median is. So wherever that cutoff is that gets to that 50%, you can say that that's the median. You can do that with ordinal data. And so in this example with the military, so lieutenant was 25.5, captain was 37. If you add those two together, we're going to get 62.5, which has that cutoff of the 50%. So it's here, but at least it gets to that 50%. So we can say captain would be the median for the ranks of officers in the U.S. Army. You can't use the mean with either one of these, the Facebook data or the military. It wouldn't make sense to use that with qualitative data. You can always use the mode. The median you can use sometimes when it's ranked. It wouldn't be appropriate, though, to do a median for unordered qualitative data, like ancestries of Americans. If you had, European, Asian, whatever it is, you wouldn't be able to get a median with that because it wouldn't make sense to do that. And you won't report a mean. You can do it when you have things that are ordered like this. So, you can't divide words, which you would need to be able to do to find a mean. So mean cannot be used with qualitative data, only quantitative. Chapter 4, this is on describing variability, basically how far spread out is a distribution sample that you have. I'm going to move to the calculations pretty quickly. So we'll go to the calculations and then maybe we'll talk a little bit about the theory. The calculation is what's on the test. Calculating standard deviations is what we're talking about. And so you'll need to be able to do that by hand on the test. Some things we'll do by hand, some things we won't. Standard deviation I think is kind of a good one to do by hand because I think by doing it by hand you can kind of see what's going on with that data. So we are looking at variability in this chapter. That's variance, how varied is the data, the spread of the data, basically how far is that data spread out. So yes, measures of variability, descriptions of the amount by which scores are dispersed or scattered in a distribution. You might think of range, but range isn't that specific, and also with range, we talked about it, some of the other chapters, outliers can affect your range. So another way to think about it, the mean that we talked about last chapter is a measure of position. So remember that president's example, that mean was 5.6, that's a measure of position where the data meets kind of like in the middle. Standard deviation is a measure of distance from that. So mean is a measure of position, standard deviation a measure of distance. And this picture kind of shows what we're talking about here. So the average here is going to be a 10. The average here is going to be a 10. The average here is going to be a 10, the mean. But the spread of the data is definitely different. There's no spread here, just a tiny bit here. And then in the version C, the data is pretty spread out. The standard deviation is going to be different for all three of these. It's going to be almost 0 here, and then it's going to be spread out to whatever it is here. So you might think, okay, why don't we just take the mean of the deviations from the mean? So if we took, how far away is this from the mean, this one from the mean, and added those up, the problem is if we add all the deviations from the mean from each data point, it's going to equal 0 no matter what you do. So for example, if we had a data set of 2, 4, 6, 8, 10, and 12, and the mean of that is going to be 7. So if you take 7 away from each one to show how far away it is from the mean, so like 2 is -5 from the mean, 4 is -3, and anyways, if you go through and do each one, then you add them up, you're going to get a 0, so it's not helpful at all. Here's another data set just to show you again, 3, 3, 5, 6, 8, exact same thing. It's -2, it's -2, it's 1, it's 3, you sum them up, you're going to get a 0. So the mean of the deviations is not useful at all. So in looking at variability, stats people generally favor the measure for variability is standard deviation. There are some other ones, but most people talk about standard deviations. And just so you know, there's going to be a slightly different formula for a standard deviation for a population and standard deviation for a sample, but we'll get to that here in a little while. The definition: standard deviation, a rough measure or average or standard amount by which scores deviate to either side of the mean. To get to that standard deviation, we're going to have to go through a few hoops here. We're going to have to get the variance, and we're going to have to get the sum of squares. And I do have the definitions here. We'll go through it. The variance is the mean of all squared deviation scores, and the sum of squares is the sum of the squared deviation scores. I know that's a lot of words, but it'll make sense as we go through here. The variance, the mean of the summed deviation scores. Back here, if we went to this example, what we can do is, since one of the reasons this equals 0 is because we have those negatives, and so if we take the negatives out, it's not going to equal 0. And so one way to get rid of those negatives is to square each one of these. And so instead of having -2, we would have 4, 4, 0, 1, and a 9. And that would be the variance by squaring each of the deviation scores. And then you can add those squares up, and you get, just like it says, sum of squares, because we've added up those squared values. But we'll go through it in each example here. This is the sum of squares. I'm just using the computational formula, and eventually I'll write out one at some point, and I'll show you how, because you can actually take the sum squares, the variance, to get the standard deviation. You just put it into one formula. This textbook, it divides it up into the variance and sum of squares. Anyways, so to get the sum of the squares, this is the formula. So okay, we have this data set, 13, 10, 11, 7, 9, 11, and 9. That's our data set. There's a very specific way to go through this. In this Excel sheet, I'll post on Canvas so you can go and look at it. But for this sum of squares formula that we have here, I'm going to go through each step. So the first step you're going to do is you're going to get your n, which is pretty easy. Assign a value to n, representing the number of scores, 1, 2, 3, 4, 5, 6, 7. And so I have that here at the side right there. On step 2, for this, we are going to get the sum of all x scores, which is going to be 70. So all we've done is we've added 13, 10, 11, 7, 9, 11, and 9 to get 70. So you can see that this is the sum of x, adding all those together. The third one, we're going to square the sum of the x scores. So that's this part right here, the square. So we're going to take that 70 times 70, 4,900. Step 4, we're going to square each x score. So square each x score. That's going to be done here. I did it to the side here. So 13 squared, 10 squared, 11 squared, etc. So square all those scores, and then on the next step, we're going to sum up those scores. That's sum of. And so we sum all those x scores. We're going to get a 722. Then we're going to take these numbers that we've been getting, and we're going to substitute those into our formula to get the sum of squares. And so we've got our 722 here that we got, the 4,900 that we got. Our n was 7. And we take that out, and we're going to get a 22. So 4,900 divided by 7, then 722 minus what that is going to give us 22. So we have 4,900 divided by 7, that gives us 700. And then 722 minus 700 is going to give us that 22. We're going to take that, we're getting close. We're going to substitute it into the variance formula, which is sum of squares divided by n. So substitutes in that formula. So sum of squares divided by n, which is 7, gives us 3.14. And then the last thing we have to do is do a square root of that. And so square root of 3.14 is 177. Okay, so I'm going to try to do one by hand so we can see what this looks like. So again, that's the population. For a sample, it's going to be slightly different. Part of the formula, it's going to have an n-1. I'll explain why that is here in a little bit, but I did want to go through an example. I'm going to do it by hand this time, and maybe that will be helpful. We'll see. There's that n-1. I'll talk about it in a bit, and n-1 again here too. So we're going to do the whole sum of squares thing. Then we are going to do the variance, and then we're going to do we'll actually get to the standard deviation. So let's say I have a distribution or sample. Sorry, let's say it's 1, 3, and 4. The first thing we're going to do, what is the n? N equals 3. So that's step 1. I can go to step 2 on this Excel sheet. I'm doing a different example here. So the sum of all x scores. All of these are going to be, so some of those is going to be 8. So sum of all x scores is 8. Then we are going to, so here's the sum of x. Now we are going to square that. So we're going to square 8 and we're going to get 64. Okay, the next thing we're going to do is square each x score. So we got a 1, a 3, and a 4. We're going to square each one of those. We'll get 1, we'll get 9, and we'll get 16. So that's part here. Then we're going to sum all those scores up, sum up. So 1 plus 9 plus 16 is 26. And then we're going to substitute our numbers into the formula. So for this one, we have that 26, and it's going to be minus the sum x squared, this one here, this one right here. So it's going to be minus 64 divided by n, which is 3. There's 64 divided by 3, 21.3. So 26 minus 21 we'll go 3 and get a 4.67. So that's the first part. That's getting the sum of squares. We're going to take that number then, and we're going to get the variance. So 4.67 divided by n-1. So that's going to be 4.67 divided by 2. We get 2.335. Let's go ahead and round that to 2.34, and then we will take the square root. That's the last step right here. Square root, and we will get square root of 2.34. We're going to get a 1. Put it up here. 1.53. So the standard deviation for the sample of 1, 3, and 4 is 1.53. So we are going to do it by hand for the quizzes and for the test, just so you know. But if you wanted to in Excel, it's not too hard. So you put in your whatever your sample is, and then you're going to put equal STD, and you have 2 here towards the top. You have standard deviation for P, standard deviation for an S. So again, there's a difference between the population and the sample. If we did the sample, which we just did, just double click that STD, that standard deviation dot S, get your numbers, click enter, 1.52. It does round to 1.53. Again, there's a little bit of rounding errors here and there. If we did it for a population, just so you can see, let's change that to I wonder if I can just put a P in there. Let's see. Yeah, it's smaller. And so one of the things that they want to do, one of the reasons why we do that n-1, why we change that denominator, is that the population we don't know exactly, but they think that possibly with the sample that it's going to underestimate the standard deviation. And so this is one of the reasons why they do it n-1. I know it's kind of complex, but the idea that it's underestimating the sample might underestimate the standard deviation is the reason why we make it n-1. So the sampled standard deviation would tend to be lower than the real standard deviation of the population. And again, when we're using a sample, what we're actually trying to do is guess what the population is. And so if that sample is underestimating that standard deviation, then they do want to make a change for that. So it's a more conservative estimate. How they get to those numbers, I don't know exactly. I think it was the first person that used this was Carl Pearson, at the end of the 1800s. And he's the one that decided that. And a lot of stats, a lot of things that we're going to talk about, you can trace back to Pearson. And it's like, okay, well, why did he do that? And it's like, that's just what he decided. You know, we'll talk about statistical significance. It's like, why is it 0.05? Oh, because that's what Pearson thought it maybe should be. And so, yeah, there's a little bit of subjectivity in statistics that we've talked about before. Okay, and so there's several reasons why we'd use the standard deviations. But one is, generally speaking, we're going to be talking about normal distributions and how the distribution's laid out as a bell curve. So if you haven't heard that before, that term, so a bell curve, it looks like this, with the majority of the scores in this area and the not necessarily outliers, but the extreme scores are here at these ends. So in this example, this is IQ scores for fourth graders. The average for them is 105. One standard deviation either direction is 15. So if we go to 90, that gets us one standard deviation this way. If 105 to 120, that's one standard deviation, 15. A lot of our scores are going to be just in this area here. The majority of our scores, in fact. So, about 68% of our scores are going to be within this one standard deviation either direction. This shaded part right here. 68% of the scores are within that. So 68% are between 90 and 120. A very small percentage of scores will be 2 standard deviations away. So in this case, 1, 2 is at 75. Going this direction is 135. So only a very small number are going to have an IQ of over 135 or under 175. And we talked a little bit about this with outliers. This is one way to maybe look for outliers. If you have a score that's 2 standard deviations away, it might be an outlier. Also, so from this one, 75 to 135, this is about 95% of the data. So 95% of the data is here. Only 5% are these extreme scores on either end. So we have about 2.5 here and 2.5 here. And this will be important later on when we're talking about t-tests and things of this nature. But yeah, 95% are 2 standard deviations either direction. Leaves us with 5%. And that 5%, if you divide it out on each end, it's 2.5. So 2.5 are 75 or under, and 2.5 are 135 or over. This is for a standard distribution and normal distribution. We are going to use degrees of freedom in the future. I just wanted to give you the definition here. It is going to relate back to that n minus 1, and when we get to a place where we can actually use this, I'll show you some math that may help you to understand this. But it is the number of values that are free to vary given one or more mathematical restrictions. Just briefly, I'll show you. When I was talking about how if we add all of our deviations up from the mean from each score, and it's always going to equal 0. If we didn't know what this last variable was, we didn't know that this last one was a 12, we actually would know that it's a 12. The reason being is because we know this is going to add to 0, and so we'd be able to figure that up. We would be like, oh, we're 5 off. So what does this number have to be? It has to be this 12, meaning that that last number cannot vary. So back to that definition, degrees of freedom. The number of values free to vary given the mathematical restrictions. So that 12 would not be able to vary. I know this is very abstract, and we will talk more about it again later on. I just kind of want to get it in your minds right now that sometimes we're going to manipulate this degrees of freedom because sometimes there are numbers that actually cannot vary because of the mathematical restrictions. And in that example, that 12, it has to be the 12 because we know all the other numbers and we know that it has to equal to 0. Okay, that's chapter 4. That's variability. We're going to do standard deviations by hand. If you have questions, please let me know.